So far, we have studied what a venturimeter is, but in common practice, it is not always feasible to install such a converging and diverging section. In order to avoid that, often one uses what is called as an orifice meter. An orifice meter is nothing but a small orifice in a tube. So consider this tube through which there is a flow of liquid from left to right, and there is an orifice like this. So there is a small orifice through which the flow is exiting. The area of the orifice is called as A naught or AO. So the streamlines come like this, they converge sharply near the orifice, and then they exit out in this fashion. So there are zones where there is a lot of loss in energy because there will be a lot of recirculation over here. Similarly, because of the sudden change in area, there will be a lot of recirculation in this region as well. So despite these losses, the orifice meter can be used to obtain relatively precise measurements. Another important aspect of an orifice meter is the fact that the minimum area of the jet is reached at a certain distance away from the orifice. And this location where the area of cross section of the jet is minimum is called as the vena contracta. It is smaller than the orifice diameter. It is because of the fact that the inertia of the jet causes the jet to keep on thinning at a certain point away, and the fact that there will be recirculation rules also give rise to this phenomenon. So the area at the vena contracta, or rather the entire cross section, we can denote as C. So C denotes the vena contracta. Let this section be 1. So now we will make use of the Bernoulli theorem to find out certain characteristics of it. But before that, let us quickly see how we can make certain measurements. So a manometer tube is connected by drilling holes at the side of the pipe, such that one end of the manometer pipe is residing upstream of the orifice. So this direction is called as the upstream direction, while the other end is in the vicinity of the section of the vena contracta. So essentially this region is measuring the piezometric pressure at the vena contracta, while this pressure is measuring the piezometric pressure at a section away from the orifice upstream to the floor. As you can imagine, the pressure at the vena contracta will be lower than the pressure at point 1. Because of this fact, the manometer fluid will be lower in this direction, in this limb, and it will be higher in this limb. Using this, we can find out an estimate of what the difference in the piezometric pressures are. So now we can make use of the Bernoulli theorem. We can write down P1 plus half rho V1 square plus rho G Z1 is equal to P2 plus half rho or not B2, we can call it PC plus half rho VC square plus rho G ZC. We can divide everything by rho G, so that we have P1 upon rho G plus 1 upon 2G V1 square plus Z1 is equal to PC upon rho G plus half 1 by 2G VC square plus ZC. So we can combine P1 upon rho G plus Z1 as the piezometric pressure, and we can write it down as P1 star upon rho G plus V1 square upon 2G is equal to PC star upon rho G plus VC square upon 2G. Now we can isolate the expressions. We can write down P1 star minus PC star upon rho G is equal to VC square minus V1 square upon 2G, and we can relate VC with V1 through the conservation of mass as AC VC is equal to A1 V1. So essentially, if we take VC common, we have 1 minus V1 square upon VC square, and essentially this becomes VC square upon 2G 1 minus, now V1 upon VC is equal to AC square upon A1 square. Now we can make use of hydrostatics in order to find out the pressure difference at sections 1 and C in terms of this particular manometric height. For that purpose, let us take this as the reference location and let this height be Z1, let this height be at the same height Z1, and let this height be delta H. That is the difference in the level of the manometric fluid between the two fluids. So let me call this as H naught. So if I equate the pressure at points A and points B, I will have P1 plus rho G Z1 minus H naught, and this will be equal to PC plus rho G Z1 minus H naught minus delta H plus rho M G delta H. So this particular expression is purely from hydrostatics, and it equates the pressure at A and B. We have done something similar to this while we have analyzed the Venturi meter. So from this we obtain P1 plus rho G Z1 minus PC, so minus PC plus rho G Z1, and this will be equal to rho G, so minus rho G H naught plus delta H plus rho M G delta H. So these two terms plus rho G H naught. I have just rearranged all the terms in the above expression. So this is essentially P1 star, that is the piezometric pressure, minus PC star, and this is equal to minus rho G delta H plus rho M G delta H. Essentially this is G delta H rho M minus rho, or if I take rho outside, it will be rho G delta H rho m upon rho minus 1. So P1 star minus PC star upon rho g will be this expression divided by rho g, because this is what the equation is, and I can divide everything by rho g. That is, I can divide it by this in order to find the exact expression that we need over here. So this, the right hand side is equal to delta H rho m upon rho minus 1. So therefore the expression is, so if we simplify this particular equation, we have Vc square upon 2g 1 minus AC square upon A1 square is equal to delta H rho m by rho minus 1. This implies Vc is equal to 2g delta H rho m upon rho minus 1 upon 1 minus AC square upon A1 square and the square root of this. So in this particular analysis, we are able to find out the velocity at the vena contracta in terms of the observed difference in the manometric height. So Vc is equal to square root of 2g delta H rho m upon rho minus 1 upon 1 minus AC square upon A1 square. Now the actual velocity that will be obtained during this entire process will not be actually this, but it will be something else. It will be lower than what we theoretically calculate. So in order to accommodate the various losses that may occur, so the various losses may be in terms of uh, the viscous losses or the eddy losses because of the flow recirculation. So those losses are accounted for through a coefficient of velocity, that is CV, that is the actual velocity upon the theoretical velocity. And this means that the actual velocity will be equal to CV times square root of 2g delta H rho m upon rho minus 1 upon 1 minus AC square upon A1 square. Now the second task is to write down the entire set of expressions in terms of the orifice area, that is A naught. The fact is we have found out the expression for the velocity in terms of the area of the vena contracta, which may or may not be known. Usually it will not be known. So another way of empirically accounting for the fact that the area at the vena contracta will be different from the area at the orifice is through a coefficient of contraction. So this particular coefficient was called as the coefficient of velocity. While the coefficient of contraction is given by Cc, and it is given as the area of the contraction divided by the area of the orifice. So AC is the area of the vena contracta. Using this, we can find out a yet more simplified expression for the actual velocity as the coefficient of velocity multiplied by 2g delta H rho m upon rho minus 1 upon 1 minus Cc square A naught square upon A1 square. In fact, the flow rate or the discharge will be Vc multiplied by the area of contractor. Basically this is CV CC A naught square root of 2GH rho m upon rho minus 1 upon 1 minus CC square A naught square upon A1 square. So this gives us an expression to find out. So this is delta H to find out everything in terms of the manometric properties. So we can simplify this further. CC A naught square root of 2G upon 1 minus CC square A naught square upon A1 square times square root of rho m by rho minus 1 times delta H. So in this particular expression, this entire thing is called as C. Simply it's written as C times square root of rho m by rho minus 1 times delta H. Moreover, rho m by rho, this will be known because this is the ratio of that specific density or the density of the manometric fluid upon the density of the working fluid, and delta H will be measured. So at the very beginning, you have to calibrate the orifice meter. Meaning, you given a certain known flow rates and you find out the delta H. Okay, so given that it's square root, so it will be something like this. So now your task is to find out the points, where do they lie, and then you have a lookup table through which you can then do a suitable interpolation to find out the volume flow rate for a given random delta H. But the key point over here is orifice meters of a given orifice area are sort of accurate for a certain flow range. So depending on the flow range that you anticipate, you will install a given orifice meter. You cannot use any orifice meter in any situation because calibration quickly will go beyond the idealized cases and it will reach limits where there will be severe non-idealities. And in order to avoid these kind of non-idealities, it is decided that one has to use a certain orifice meter of a certain area in certain applications. All this is valid as long as these coefficients, these ad hoc coefficients, are not too deviant from the value of 1. Once they start deviating significantly from 1, that implies that the idealities have been lost significantly, meaning there are enough viscous losses or there are enough recirculation losses in the flow situation to render this entire experiment futile. You have to redo it with a certain different orifice, which will sort of obviate some of the issues arising from this particular orifice size.